Hi again. This is Unit 4, Part 2. In Part 1, we learned how to find the posterior distribution of a population proportion when we have no information about the population proportion. There is no previous study, and we have no knowledge about the population proportion. We cannot say which value has higher probability compared to some other values. But now we need to learn something else. We need to learn how to find the posterior distribution when we have some information about the population proportion. There is some previous study, or you believe that the population proportion maybe it is equal some specific value. So we need to talk about more alternatives for the prior distributions, and how do I update the prior distribution with the likelihood and see what is the posterior is what. And also we need to learn how to compute or graph the posterior distribution. So again, in Part 1, we drove the posterior distribution under uniform prior, but now we need to discuss some alternatives like the conjugate prior. So we need to know, what do we mean by conjugate prior? Does uniform distribution is a conjugate prior? Is not a conjugate prior. So what do we mean by conjugate prior? If the prior and the posterior distribution are from the same family, the prior is called the conjugate. What do you mean? I mean, if the prior distribution is normal and the posterior is normal, so this prior distribution is conjugate prior. If I use a prior distribution as beta, and I found the posterior is beta after I multiply the prior by the likelihood, I get beta posterior distribution. So now they are from the same family. So the beta distribution as a prior is called the conjugate prior. So how do I find a conjugate prior for some parameter? Like in our case, we are working with population proportion. How do I select a conjugate prior for the population proportion? One commonly used method for constructing a conjugate prior distribution for a parameter involves identifying the distribution whose kernel aligns with the likelihood function, and then select a prior distribution from the same family. So do you remember when we looked at the kernel of the likelihood? We found the kernel is beta. So we can use conjugate prior as beta distribution. And then when I multiply the conjugate prior as beta by the likelihood, for sure I will get a beta distribution as posterior distribution. If this is something important, this is very important, because I want to make sure that the posterior is known distribution. If it is known distribution, like beta distribution, gamma distribution, normal is one of the known distributions, it is very simple to do estimation and inference, because everything is known about this known distribution. So let's think about the conjugate prior for the population proportion again. Regarding the binomial example, recall that pi must lie between 0 and 1. And we know that note how the parameter pi appears in the binomial likelihood. We found that pi is raised to some non-negative prior, and 1 minus pi is raised to some non-negative prior. So the likelihood is a kernel of what density function? Beta distribution. So it is the kernel of beta distribution with fixed parameter alpha and beta. So we can use a prior distribution for pi as beta distribution with some alpha and beta. So what is alpha and beta? I will show you how to find alpha and beta. But now we need to talk about the conjugate prior for the population proportion is beta. So I can use this one rather than using the one we used in Part 1, which is probability of pi is 1. And pi is between 0 and 1. So we use this one in Part 1. So let's use this one in Part 2. And see the posterior distribution will be what? If I use beta distribution as a prior distribution for the population proportion. For sure it will be beta, because this is conjugate prior. So let's familiarize ourselves with the beta distribution as a prior distribution. As I said, on our Canvas page, I listed a link for the probability distributions, and I listed many probability distribution. click on some of them and familiarize yourself with the shape of the distribution, the function of the distribution, the mean, variance, and so on. So those are some graphs for the beta distribution at different values for alpha and beta. If you use alpha and beta equal 0.5, it gives you this one. If you use alpha is 5, beta is 1, it gives you this one. If you use alpha is 1, beta is 3, it gives you this one. See, everyone, it gives different probabilities for different values. If you use this red one, it means you give low likelihood for these values in the middle and high probability for the small one, high probability for the big one. Looks like I believe that the value of the population proportion is very small or very big. I don't think it is something in between. If you use the green one, it means you believe that the probability, the values for pi is small values, not big values. Looks like this one works for our example, because most probably the proportion of students who will quit school is not something like 0.6, 0.8, 0.9. It looks like some value here. If you use the blue one, it means the proportion of students who will quit school is very big, because I gave higher likelihood for these big values and a small likelihood for the small values, and so on. See, so you need to select the ones that match your beliefs or the one match your previous study. I will show you how to do it. So now let's drive the posterior distribution under a conjugate prior, which is beta distribution. This is the beta distribution. This is the conjugate prior. I can get rid of the constant because I don't care about the constants. So the prior distribution for the population proportion proportional to this part. So now I can use the Bayes rule again. We will use this one a lot during the semester. The posterior distribution of the parameter I'm interested in, given the data proportional to the prior distribution of the population proportion pi times the likelihood. You can write down L of pi semicolon y, or you can write given y. It's up to you. So now this one is beta distribution and this is the likelihood. Let's multiply these two and see the posterior is what. This is the kernel of the prior distribution, everything function of pi. And this is the kernel of the likelihood, everything function of pi. Let's multiply these together. You get this one. So this is kernel of what? For sure it's beta, because I use the conjugate prior. So what is alpha for this posterior distribution and what is beta for this posterior distribution? Because it's beta distribution. The new alpha is this one. The new beta is this one. So this is a kernel of another beta density function with alpha star, beta star. Alpha star is alpha plus y. Beta star is beta plus n minus y. So now if I used alpha is 0.5, beta is 0.5, so alpha star will be 0.5 plus y, and the beta star will be 0.5 plus n minus y. Looks like a 0.5 plus number of successes, 0.5 plus number of failures, and so on. So I want to show you how to find alpha and beta. But let's write down this function first. Write down the density function. So it is beta distribution with alpha star, beta star. So the probability of pi given y can be written as gamma alpha star plus beta star. You need to calculate alpha star, beta star for some specific example. Gamma alpha star, gamma beta star. If you don't know what is gamma, gamma 7 is factorial 6. Gamma 5 is factorial 4, and so on. So times pi to the power alpha star minus 1 times 1 minus beta pi to the power beta star minus 1. Keeping in mind the range for pi is between 0 and 1. So let's simplify this formula, because we know alpha star is alpha plus y, beta star is beta plus n minus 1. So this one is gamma alpha plus y plus beta plus n minus y divided by gamma alpha plus y times gamma beta plus n minus y times pi to the power alpha plus y minus 1 minus pi to the power beta plus n minus y minus 1. So this one will cancel with this one. So it gave me gamma alpha plus beta plus n divided by gamma alpha plus y divided by beta plus n minus 1 times pi to the power alpha plus y minus 1 minus pi to the power beta plus n minus y minus 1. And after you collect the data, plug in y and n, and you need to assign some value for alpha, some values for beta, and then now you would know the exact formula for the population, for the posterior distribution of population parameter. But you don't need this one because everything is known about this beta distribution. So for example, if I need to estimate pi, you get the pi hat using the mean, like posterior mean. It is known the mean of the beta distribution is alpha divided by alpha plus beta. So alpha star plus beta star. So this one is alpha plus y divided by alpha plus beta plus m. So this is the estimation for pi hat, or estimation for pi using the Bayesian approach when I use a conjugate prior beta distribution. If I'm interested in the variance of the estimator, it is called variance or posterior variance. This one equal, I know the variance of this distribution as well. The formula is alpha star times beta star divided by alpha star plus beta star square times alpha star minus beta star plus 1. Guys, please, I think this one is plus. Okay, double check, but I think it's plus. Now let's plug in all these values. Alpha star is alpha plus y times beta star is beta plus n minus y divided by alpha star plus beta star, alpha plus y plus beta plus n minus y square times alpha plus y plus beta plus n minus y plus 1. So this one cancel with this one cancel with this one. So the variance of the posterior distribution is alpha plus y times alpha plus n minus y divided by alpha plus beta plus n square times alpha plus beta plus n plus y. This is the variance. Because what is the meaning of the variance? Because everything, there is nothing accurate with 100%. Like I will estimate pi hat by this value, but this value is different for the population proportion. How much is this difference? How much is different from? What about the variability? So the variability can be calculated using this formula. Or you can explain this one in a different way. When you graph this function, let's say the graph of this function is this one. The mean of this function is this one. The variance of the distribution or the variance of this function is this one. So it can be explained in a different way. So before we move on, how do we choose alpha and beta for the prior distribution? Because we use the conjugate prior, and the conjugate prior is a function of alpha and beta. How do I choose alpha and beta? I can choose alpha and beta based on my beliefs about the parameter as a researcher, or I can use alpha and beta that match some previous study. So we need to learn how to do. I will show you some methods that can be used to select alpha and beta. So let's go over some methods. Here are several ways to think about this, choosing the parameters of a beta distribution, alpha and beta, to express prior beliefs or previous knowledge about the population proportion. The first one, you can graph many beta densities and look at them and see which one match your beliefs. Like these ones, see, we graph the many of them and you see which one match your beliefs as a researcher about the population proportion. Or if you have a previous study, use alpha minus 1 equal number of successes and beta minus 1 is number of failures. Why? Because when we look at the kernel of the likelihood, when we looked at the likelihood, we found that the number of successes is alpha minus 1 and number of failures is beta minus 1. This is why they came up with this formula. I mean, if there is some previous studies that they selected a sample of 100, and they found number of successes as 20 and number of failures is 80. So now I can use this information to make a conjugate prior by selecting alpha equal 21, because alpha minus 1 equal 20, so alpha equal 21. And I use beta equal 81. So this is how I use previous study to make a prior distribution. So now I can use a beta distribution that has information equivalent to a sample of 100. And the number of successes is 20, number of failures is 80. This is how to use previous study to make a conjugate prior. Because we found that in the likelihood, when we looked at the likelihood, we found it is a kernel of beta, and alpha is number of successes plus 1, and beta is number of failures plus 1. This is how they came up with this formula or this strategy. Another strategy, you can select the prior distribution, you can select alpha and beta that give you some specific mean. Because maybe you believe that the pi is something like 0.2. So you can use one of the equation is alpha divided by alpha plus beta equal 0.2. But this is a function, is equation in two unknown values, alpha and beta. I need another equation to solve the two equations to find alpha and beta. So you need to assign some desired mean and some equivalent sample size, because from this formula, we can see that the sample size equal alpha plus beta minus 2. This is a condition. When you add the number of successes plus the number of failures, it gives me the sample size. So the sample size equal alpha plus beta minus 2. This is another equation that can be solved with the mean equal some desired value. And you find alpha and beta. Something like, I would like to have a conjugate prior beta distribution with mean equal 0.2. And the information in this prior distribution is equivalent to the information is in a sample of 100, for example. So now I have two equations, alpha divided by alpha plus beta equal 0.2 and alpha plus beta minus 2 equal 100. So now I can solve this equation to find a prior distribution that the mean of this prior distribution is 0.2, and the information in this prior distribution equivalent to the information in a sample of 100. Because keep in your mind, there are many beta distributions with many different alpha and beta that gave me the same mean 0.2. So I need to select one of them. So we need to have another condition. So another strategy, choose values of alpha and beta that produce a prior probability interval that reflects your beliefs. You think about the interval. You think about the pi in the population between two values with some confidence level 95. So, or with some probability 95, because I work with a distribution. So you can graph many ones with the same probability or the 0.95, and see which one match your belief. Let me go over all these ones, but applied or our motivating example. So, and let's talk about these ones before. The new data must not be used in any way in constructing the prior density. This is very important in Bayesian, because the likelihood and the prior should be independent. This is why I multiply these together to get the posterior. But if they are dependent, this is a problem. So when you select the prior distribution parameters like alpha and beta, you shouldn't look at the data. So the new data must not be used in any way in constructing the prior density. We will see shortly why that would make inference invalid, actually. Let us apply the first four strategies to our motivating examples, assuming we selected a sample of 50 students. So the first strategy is graph many of the beta distribution, like this is beta 1040, this is beta 10, 5, 10. This beta alpha is 20, beta is 10. This is beta alpha is 2, beta is 2. Which one match your belief? When you look at this one, looks like you give higher likelihood to the values about 0.2, and you give a very small value or almost 0 to something greater than 0.4. Looks like you believe that the proportion of the students who quit school after raising the tuition by 20%, no way to be greater than 40%. It is something here. If you choose this one, you add more values. If you choose this one, you change you almost give some values for everything. All the values have some probability, but the values about 0.5 is big. And this one, the values about 0.7 is big. This means you believe that the proportion of the students who will quit school is very big. Is not small. Like it's not no way to be 0.10, no way to be 0.30, something like greater than 40%. So as a researcher, you think about these prior distribution and select one of them. If you don't like this way, you work with another strategy as a researcher. If we have a previous study, use alpha -1 equal number of successes, beta -1 equal number of failures. So we wish to use any relevant data available before we do our survey. Suppose that we read that such a survey has already been taken at Iowa State University, in which they also selected 50. It's not necessary to be the same number. Selected 50 students were interviewed, and they found 10 said yes, they will quit. So it means 40 said no. So number of successes is 10, number of failures is 40. So using this strategy, I will use alpha equal 11, beta equal 41. So this is a way of selecting the prior distribution as conjugate prior based on previous study. So the probability of pi proportional to, I use only the kernel, I don't care about the canister. So probability of pi proportional to number of successes minus 1, number of successes to the power number of successes, 1 minus beta to the number of to the power the number of failures. This one is alpha -1, this is alpha, this is beta -1. The mean of this density function is what? It looks like I believe that the pi is some value very close to alpha divided by alpha plus beta is 10 divided by 10 plus 40. So it is 10 divided by 50 is 0.2. This is a graphical representation. It gives high probability or high likelihood to the values very close to 0.2, small values for the others. So maybe this one matches your beliefs. or this one using previous step, and you feel like is okay to use it. Another strategy is that you set some conditions, like the desired mean is some value and the equivalent sample size is some value. So for example, say that we want a prior about the prior mean 0.2, but there are many functions have the same prior mean 0.2. There are many alpha and beta give me the same mean. So the same as the sample proportion from the Iowa State University, but an equivalent to prior sample is smaller than 50. Looks like I feel like, because if I use the sample size is 50 and the mean is 0.2, a number of successes is 10, number of failures is 40. Maybe this means you will use a prior distribution, has information equivalent to a sample size of 50 with mean 0.2. Maybe you feel like, I like to use the prior mean 0.2, but it comes from a sample is smaller than 50. When you choose a smaller sample size, it means you do not feel confident with the mean. But if you use a higher sample size, it means you feel more confident about the mean. Let me show you this idea. All these four have the same mean 0.2. But this one looks like the variability is very small. When you use alpha is 10, beta is 10, it means the sample size is what? Alpha plus beta minus 2. So the sample size is 48. So when you use the prior distribution, has information equivalent to a sample of 48, it looks like you are believed that it is very close to 0.2, more than using alpha is 1.25, beta is 5. And the sample size is 5 plus 1 is 6, 6.25, so 4.25. I know there is no 4.25, but something like a small sample. So all of these ones give you the same mean, but they have different alpha and beta, and they have different sample size. So a smaller sample size means you do not feel confident. The higher sample size means you feel more confident about the mean, and so on. The last strategy is that you graph many density functions with 95 central interval, and for example, this one was alpha is 10, beta is 40, and this is the 95 probability. So you believe that the value is 95 probability. 95 probability is between these two values. Or this one, this is a wider confidence interval, or the higher, the higher confidence interval. And this one is more higher, this one is more higher. And all of them are, you believe that it is between these two values with 95 probability. You believe it is between these two values with 95 probability. You believe it is between these two values, and so on. So you need to select the one that match your beliefs. So let's go back to our example again. Assuming that Virginia Tech has decided to raise the tuition by 20%, what is the proportion of the students who will quit school? No way to work with the population is big, so you decide to work with a sample of 50 and to see, and you would like to estimate the population proportion using the sample using Bayesian approach, and also maybe you are interested in these two statements to see which one is correct. So assuming I'm going to work with a conjugate prior, beta, with alpha 10, beta 40, alpha 10, beta 40. So in this case, I will work with the alpha 10, beta 40, and then the next step is collect data, assuming I selected a sample of 50 and found y is 7, so n minus 1 is 43. Let's plug in all these information, alpha, beta, y, n minus y, in the posterior distribution that is proportional to this one. And then it will be proportional to this one. So this is beta 1783. You don't need to do it every time because you know that if I use the beta distribution as a prior distribution, for sure, the posterior distribution will be beta distribution with alpha star, beta star. I don't need to do these ones every time because it is known that if I use beta distribution as a prior distribution, the posterior distribution will be beta with alpha star, beta star, and alpha star is alpha plus y. Beta star is beta plus n minus y. And I know alpha is 10, beta is 40, n is 50, y is 7. You plug in these values, you get beta equals 1783. You don't need to draw the formula every time because it is known. Now it is known for us. It is known that if we use the prior distribution as beta distribution with alpha and beta, the posterior distribution will be beta with alpha star, beta star. So for example, if I use another beta like 1.25 and 5, you don't need to draw these ones again. It is known. You plug in the values in this one, you find the posterior is this one. If I would like to calculate the mean of this one, is alpha divided by alpha plus beta. The mean of this one is alpha divided by alpha plus beta. This is the estimation of the population proportion using Bayesian approach under conjugate prior and so on. How do I graph these three functions to have a nice graph? Like I would like to graph the prior, likelihood, posterior. There is a function in R, is called triplot. This function can be used to graph the three ones. So what should I give to this triplot function? First, we need to install the package learn Bayes because this function is not a built-in function in R. So you need to install this package first and then library. And sorry, if you'd like to have some help about the triplot, write help. And it is very simple. You write down the function and you give the information about the prior, information about the data, or the likelihood. For the prior, let's use alpha is 2 and beta is 10. And for the likelihood, I use y is 7, n minus y is 43. And this is the information about the prior. This is the information about the likelihood. The function will use this information to find the posterior and graph the three functions. This one is the prior with alpha 2, beta 10. And this one is the blue one is the likelihood, and the red one is the posterior distribution. So this function can be used to graph the three functions. So let's have some notes about the relationship between these three. The prior, likelihood, posterior. I graphed the three under beta prior 10, 40. A number of successes is 7, number of failures is 43. I graphed the prior beta 520. I used the smaller alpha, smaller beta, but the same number of successes, the same number of failures. I make a smaller values for alpha and beta, smaller values for alpha or beta. And I graphed the three distributions, or the three functions. In all these cases, you will find the posterior density is more concentrated compared to the prior and likelihood. This one has less variability compared to these two. This one has less variability compared to these two. This one has less variability compared to this one. The same thing here. Why? Because the posterior distribution contains information more than the prior, more than the likelihood, because it combines the information for the two resources and it gave me something has less variability, less uncertainty. So this is why I see the posterior has less variability or less uncertainty or more concentrated compared to the others. The less information prior, the more the data dominates the posterior. This one, the prior has less information compared to this one, So when this one has less information, the likelihood will dominate the posterior because the information from the likelihood will be higher than the information in the prior, which is logic, expected. Guys, if you have any question, please let me know. And what is next? We still need to know how do we use the posterior density function to estimate the population